Okay, I think we can start. Good morning, everyone. Welcome to the first DRYvER webinar. So the theme of this first webinar will be modeling of streamflow intermittency in DRYvER networks. Sorry. So it's the first webinar of a 5-webinar series in the frame of DRYvER project, which was funded by the European program Horizon 2020. So for those who don't know DRYvER yet, it's a project that investigates how biodiversity, ecosystem function, ecosystem services and their value in DRYvER networks are directly and indirectly altered by climate change. So for this, the work is divided in several work packages. And today, Louise and Petra will present us some results of the first work package. So thank you for coming. And now let's hear Louise and Petra. Sorry, I will share my screen. Can you see my screen now?
Yes. And can you put your presentation mode, maybe, so that we can see the slides bigger?
Well, no. Since it's a PDF, I think this is the presentation mode, actually.
Mode plan. Plan is you can put it on plan mode. Mode plan account.
Oh, sorry. Yeah, is it better now?
No.
No, it's the same.
Okay, I will share again the screen. Okay. You can go now, right?
Yes, perfect. Thanks. Thank you, Margot. So as our presentation will be divided in 2 presentations, I will start with a common introduction for Petra's presentation and mine. So yes, as an introduction, yes, we can start to ask what are intermittent rivers, and here you have an example of pictures that were taken in the Albarine River in France on the same location, but on different days in the year, and you can see that it's a river that have different flowing conditions. It's sometimes flowing with high discharge, and then you can have low discharges, and it can get completely dry for natural causes. So intermittent rivers are rivers that dry some part of the year, so it can be from 1 day per year to until a few weeks or even months of drying. And yes, can you change the slide, please, Margot? Thank you. And why we are interested in intermittent rivers is that they represent actually a large part of the world river, and this is a result from a paper from Messager and al. That showed that more than half of the world river are actually non-perennial, which means that we also need to investigate on intermittent rivers. Next, please. And in the DRYvER project, we're also interested in the impact of flow intermittence on biodiversity and ecosystems, because the water level and the duration of drying can have an impact on the species that live inside the river or nearby the rivers. And you have some terrestrial and aquatic species that are adapted to intermittent flow regimes, but that can be endangered when the drying periods are increasing, or other species that are adapted to live in perennial streams, and that can be endangered if some reaches start to become intermittent. Next, please. So the DRYvER project is a multidisciplinary European project on driving rivers and climate change. And so, as Margot said, it's a multidisciplinary project involving researchers from different backgrounds, such as hydrology, ecology, biology, and economy of the environment. And the objectives of the project are to study the impact of climate change on drying river networks and also to evaluate the consequences of drying on biodiversity and ecosystems. Next, please. And today with Petra, we will show you the work we did in the hydrological modeling of stream flow intermittence. And our objective was to analyze the spatial temporal patterns of stream flow intermittence in past and present period in Europe, and also to evaluate some projections of stream flow intermittence under climate change scenarios. Next, please. And so today's webinar will be divided in 3 parts. I will start a first presentation on the modeling of stream flow intermittence under climate change in 6 European study cases. And then Petra will present you her work on the high-resolution modeling of stream flow intermittence for all of Europe. And then we'll have time for discussion. So for the first presentation regarding the modeling in the 6 European study cases, so it was a work that were conducted with my colleagues from INRAE in Lyon in France and my colleagues from the Friedrich Schiller University in Jena in Germany. So in DRYvER, we are focusing on 6 study sites in Europe that are catchments that have areas between 100 and 350 square kilometers on average. And you can see on the maps that we have so one site in the south of Spain, one site in France, in Croatia, Hungary, Czech Republic, and Finland. So we have various hydroclimatic conditions represented in our study sites, and also different types of drying and causes of flow intermittence. Some sites are mostly drying due to climatic drought, other it's due to geological conditions and with the rivers infiltrating in the soil. And in some sites, we have some drying that is also caused by water abstraction. So to do the flow intermittence modeling, we started using distributed hydrological model called J2000, and it's a spatially distributed model with a process-based representation of hydrological processes. And you can see on the example of the Albarine catchment here on the map on the right, we discretize the catchment into hydrological response units, which are the small areas in colors, and the model computes the hydrological fluxes vertically from the atmosphere with the vegetation, soil, and groundwater, and then does the lateral routing of water flows from one HRU to its neighbor HRU until the water reaches a stream, and then the model does the routing of the water flow through the river network. So, next, please. So to do the hydrological modeling in the 6 European catchments, we use harmonized input datasets. We mostly use some datasets that were available at the European scale. So, for example, for the DM, we use mostly the EU DM. For climate data, we use the ERA 5000 dataset, Core land cover for the vegetation, Soil European database for soil, and IHME for groundwater. Next, please. We calibrated the hydrological model using a multi-gauge and multi-objective calibration method So here you have the example for the Albarine catchment in France, where we had 3 gauging stations that we could use for calibration and validation. And we try to optimize the model to have the best performance for the 3 stations. And we consider a set of criteria for validation. It's not only the Klein-Gupta efficiency, but we also considered indicators for low flows. And on the right, you have an example of the comparison between the observed runoff and simulated runoff in the Saint-Rambert station, which is the station in the middle of the catchment on the validation period. Next, please. And here on the right now in the table, you have also the performance for the 5 other catchments during calibration and validation. So you can see that we have different performances regarding the catchment, which is mostly due to the fact that in the calibration we did not only consider the kg but also other indicators. So sometimes the kg in validation is not so high, but the model performs better on other low flow indicators. And also because we had several stations in the catchment, and sometimes also the performance is better for other stations than the station at the outlet of the catchment. Next, please. So at this stage, once we have our hydrological model which is calibrated, yes, this one, please. We can simulate the discharges at daily time step for every reach of the river network. And here you have an example of the simulated discharge in the reach that is colored in red in the map of the French catchment on the right side. And we compared the simulated discharge with observed data of the state of flow we had in this reach. So in this reach, we had a camera that took pictures every day. And from this picture, we could tell if the river was actually flowing. So these are the points in purple, or dry, which are the points in orange. And we can see that in some periods, we have some simulated discharge, which is not equal to 0. And also here, but I don't see if you can see it very well. But actually, the river was dry. So here we can see that the hydrological model is not enough to really simulate the drying period in our river networks. So next, please. So that's why we build a flow intermittence model combining the hydrological model that I just showed you with the J2000 model with a random forest classification model. And to do that, we use as input data to the random forest model the simulations of discharge and base flow at daily time step and for every reach in the catchment, as well as climate data to give some information regarding the meteorological conditions in the previous days, such as precipitation, temperature, and evapotranspirations, and also information regarding the physical characteristics of the reaches, such as drainage area, the slope, the types of land cover, and geology around the reach. So we use these 3 types of input data inside the random forest, and then we train the random forest with flow intermittence observations. And in the output, we can predict the flowing condition. So it's a binary output. It's either flowing or dry at daily time step for each reach of the river network. Next, please. And here, if we look again at our example in the reach in the Albarine river network, now we can see in red the output of the random forest model. It's the red line, and if it's high, it means that the random forest model predicts a flowing condition, and if it's low, it's dry. And then you can see that with the random forest, now we can predict better the days with dry conditions, and the model can also be used to extrapolate the state of flow in periods when we don't have observed data. Next, please. So to train the random forest model, we needed some flow intermittence data, and we collected flow intermittence data between 2005 and 2021 in our study catchments. And we used different types of sources of data because we needed as much data that we could get to train the random forest model. So we used data coming from crowdsourced data, so that come from a smartphone application such as the DRYvER application that was developed inside the DRYvER project, but also the CrowdWater application. For some catchment, especially the Spanish catchment, we also use data from Google Earth images because in our catchment in south of Spain, there's very low vegetation, and from the satellite images, we can see if the rivers are actually flowing or dry. We also used data from hydrological stations. So these are the points in, for example, in red here in the Albarine catchment. So for stations, we have not a lot of stations in the catchment, but we have very long time series of data. And we also use, yes, this one, please. Data coming from the field campaigns that were conducted inside the DRYvER project. So these are the green points here. We have around 10 sites per catchment. It's a site where there was some cameras taking pictures every day from, depending to the catchment, from 2 months to up to 4 years, I think. And we also use what we call the expertise data that are actually the yellow points here on the map that are some sites that are part of the sampling sites inside the DRYvER project. Are sites where our colleagues also go to collect some samples, but they are perennial sites where we don't have actually photo traps data, but our colleagues that are expert on this catchment, they know that the ridges have a perennial flow here, and that these sites never dry. Next, please. So here you have also the distribution of the observed data for the 5 other study catchment, and you can see that we have different spatial coverage regarding the catchment, and we also have different temporal coverage of observed data. Next, please. And so then we try to evaluate the performance of the random forest model. So to do that, we trained the random forest 20 times with samples containing 75% of the observed data, and we tested the model on the remaining 25%. And we looked at 2 indicators to evaluate the performance of the model. First, the probability of prediction of a drying event, and also the false alarm ratio, which is the proportion of drying events that were wrongly predicted. And so you can see that on the left side of the graph, for the probability of prediction, that we have 4 of the 6 study catchments that have a probability of prediction that is higher than 90%. And for the false alarm ratio, these 4 catchments have a false alarm ratio that is around 5%, which means that they are in average 5% of the days that are simulated as dry, whereas they were actually flowing. And for 2 catchments, the Croatian catchment and Spanish catchment, we actually have lower performances, which is actually due to a smaller quantity of observed data to train the model, so a higher uncertainty in the results. Next, please. So now that we have our hydrological model and flow intermittence model, we can use the model to simulate the flow intermittence in all the reaches of our catchment and study the patterns of flow intermittent. And here you have example of spatial pattern of flow intermittent in 3 of the study catchment, the French, Spanish, and Finnish catchment. And you can see that we have quite different spatial patterns of flow intermittent in these 3 catchments. In the Albarine catchment, which has temperate climate, we have some dryings mostly in the upstream part and the downstream part, which is due to the seepage of the river inside the kartic soil for the upstream part and moraine deposit in the downstream part. And for the Renal catchment in Spain, the drying mostly occurs in the smaller tributaries, and the drying occurs after periods of with no precipitation. And you can see that there are also a lot of drying downstream, in the downstream part of the catchment, and even in the main Renal River. And this drying is due to water abstraction for irrigation. And for the Finnish catchment, here you can see that as it has a more humid climate, we have mostly perennial reaches, except for the small tributaries that sometimes can dry a few days per year. Next, please. We also had a look at the seasonal pattern of flow intermittence, and on this graph, you can see the fraction of dry river networks through the year. So from 1st of January until 1st of December. And you can see that across the catchments, we have different intensities of drying that occurs mostly during the summer. And we have a sort of gradient of intensity of drying with a strong intensity of drying for the Spanish catchment and low intensity of drying for the Finnish catchment. And you can also see that for some catchments, especially the Spanish catchment and Croatian catchment, we have some drying in this winter season as well. Next slide, please. And we had a look at the evolution of the fraction of the river network that is intermittent through the period from 1980 to 2021. And we can see that there's an intensification of snow intermittence, particularly during the last decade, and mostly in the we can see a significant trend in the Albarine River in France, the Butišnica River in Croatia, and Velishka River in Czech Republic. Next, please. So after analyzing the flow intermittence pattern in the past and present period, we also produced simulations under climate change scenarios. And to do that, we use climate prediction data from 5 CMIP6 GCMs models that were collected on the ECMIP project. And we decided to analyze 3 different scenarios of greenhouse gases emissions. So on the right, you have the 5 SSP scenarios that were considered in the IPCC reports. And here in this study, we chose to analyze the SSPs 1, 3, and 5. And we conducted a climate downscaling with the analogy method to obtain high resolution projections. And we use the downscaled climate data as input data of our flow intermittence model to simulate flow intermittence. So during the historical periods from 1985 to 2014, and for future projections starting in 2015 until the end of the 21st century. Next, please. So first I will show you quickly some results about the change of climate in the 6 catchments. So here you have the evolution of temperature so I will always show results for the scenario SSP3 7.0, and you can see that there's a strong increase of precipitation for the 6 catchment with, in average, an increase between 4 and 5 degrees regarding the historical period by the end of the 21st century. Next, please. Regarding precipitation, we have different trends for the 6 catchments. For the Spanish catchment, for the French catchment, and for the Hungarian catchment and Croatian catchment, we have negative trends of precipitation with decreasing precipitation through the future years. And for the Finnish catchment, we have a slight increase of precipitation. Next, please. And regarding the simulated discharge, here we have a decreasing trend of discharge for the 6 catchment with different intensities. You can see that we have a very strong decrease of discharge in the Bukovsdi catchment in Hungary, as well as in the Renal catchment in Spain, and Velicea catchment in Czech Republic. But we have a negative trend in the 6 catchments. Next, please. So last results are regarding the projection of flow intermittence. And here you can see some maps showing the difference of number of dry days per year between the historical period and the last 30 years of the 21st century for the French, Spanish, and Finnish catchment. And you can see there's quite a strong increase of flow intermittence in these 3 catchments. But the maps also show a limitation of the random forest when we use the random forest model to extrapolate in the future, because we have an increase of drying events only on the reaches that are already intermittent today during the training period of the random forest. And you can see for the Albarin catchment and the Lepsämäenjoki catchment in Finland that the random forest cannot simulate some drying events in the reaches that were only perennial during the training period between 2005 and 2021. So this is kind of a limitation of using models such as the random forest model to extrapolate in the future, because here we cannot really analyze a spatial expansion of flow intermittence. But it's still interesting to evaluate the evolution of flow intermittence in reaches that are already intermittent today. Next, please. And last result is to show you the different projection of the seasonal pattern of flow intermittence across the 6 catchments in Europe. And you can see a strong increase of the length of the dry river network due to climate change, and it concerns all seasons, but it mostly occurs. It mostly have the largest impact on summer. And you can see that we have seasonal patterns very specific to each catchment study site. Next, please. And I will finish on this slide showing that we developed an application that is called DRYvER Hydro that you can find online on this link. And it's an interactive tool where you can explore all the simulation results that we produced for the 6 catchment for the present period and in projections, to see how the through intermittence is changing through time and for the 6 catchments. So do not hesitate to visit this application. So that's it for me, and I leave the floor to Petra.
Thank you, Louise. While Margot is sharing the screen, I can already start with telling you that now we will move to a very different scale. Margot, will you be sharing the screen?
Yes, 2 seconds, please.
Yeah, sure. Take your time. I will already start talking because we're a little late in time. So I will talk about high resolution modeling of streamflow intermittence for all of Europe. And just to give you an idea about the different scale that we're at. So Louise mentioned that the Albarine Basin is 350 square kilometers. And when we look at this area of Europe, that's more or less 20,000 times more of space, now a few million square kilometers. So here we're trying to estimate for each month in the period 1981 to 2019. First of all, in a first step, was it a month where there was at least one day without any flow? And then in the next step, we also try to say, okay, we have then 5 classes for the intermittent month. We can say then, is it 1 to 5 days of no flow in this month, or 6 to 15, or 15 to 29, or is it the whole month? So this is the goal to do this for Europe. And you here see a map of our results. So I will not be able to tell you anything about climate change because we have not reached that yet. But I will tell you the work that I did together with Mehdi Abbasi, Tim Troutman, Mathis Messager, Bernhard Lehner, and Nicolas Lamoureux to come up with an estimate of a high resolution picture of streamflow intermittency, but a dynamic one. Because what we saw on the first slide by Louise, who showed this global map, that was a map that was done by Mathis Messager, one of our colleagues here. But in the global scale, what he managed to say is, okay, this river, at least in one day in 30 years, it was dry. But here is a very different thing. For just the European scale, we say for each month, is that month a dry month? And in 4 classes, if it is an intermittent month, how many days? Okay, so this is already now the result for what is the percentage of the month with 0 flow days. So in blue, you see all the rivers that we estimate to be perennial. And then everything that is from yellow to red, that shows the percentage of months with no flow days or 0 flow days in the time period 1981 to 2019. And you see, of course, in Spain, there's a lot of intermittency, and this is the major, but also in France, where the Albarine Basin is, that Louise presented quite a bit in her presentation. Next. Yeah, so just where the green is, we will zoom in now, just so you give you an impression at what scale we are. Next. So, yeah, so this is just a zoom in into the map that shows again the perennial and non-perennial reaches. So whatever is blue is perennial. And then in this yellow, I mean, you see yellow means it's maybe 0 to 10%. It means according to our model, is 0 to 10% of those yellow stream reaches is intermittent. So here you see more, you see here 10 to 20 kilometers, you see the scale there. This is the resolution of our modeling approach. Next, please. So for this high resolution modeling, we need to do 2 steps, and they're not very, I mean, they're in a way similar to what Louise presented, that we start with a hydrological model, and then we use random forest modeling. But you will see that still, because of the scale and because of the very different information input that we can have for such a large area like Europe, as compared to these small drying river networks, small basins, it is very different. No, and we cannot be as precise, obviously, than if you work at the small scale. So what did we do first? We used the output of a global hydrological model, the model water gap. This is a model that has been developed at my group for more than 25 years. And this model works at a very rough, for Europe, a very, very coarse resolution, half degree by half degree. This is approximately 50 by 50 kilometers. And we will call that from now on low resolution. And this model that produces various outputs. And this output is then used to obtain time series of monthly stream flow. So monthly, not daily, like in Louise's case, of monthly stream flow at the spatial resolution of 15 arcseconds, which is approximately 500 meter resolution. And of those 500 meter grid cells, there are 73 million of those high resolution grid cells in Europe. And so we need to downscale the information of our low resolution global hydrological model from 50 by 50 kilometers to 500 by 500. And that means a downscaling by a factor of 14,400, because there's just 14,400 small cells, high resolution cells, and one large resolution cell. So this is the first step that we did. Then we used the downscaled monthly stream flow time series. So for every single month between 1981 and 2019, we used that, similar to what Lee said, as an input to a random forest model, but at the monthly scale. So then the second step, the random forest modeling, is there to estimate monthly time series of the number of no-flow days in 5 classes. So either 0, so perennial, or these other 5 classes that I've already told you. And then we estimate that not for every single cell at the 500 meter resolution, because the 73 million, that's too much. We do that for reaches. So we derive reaches, similar to what also Lee said. And we have identified 1.5 million reaches. So how do we do that? We look at all basins that are larger than 2 square kilometers. So that's the minimum size that we use. So we have as input to the random forest modeling, the stream flow estimates, but then also other predictors that are also physiogeographic predictors. Next slide, please. So in this type of, that's fine, that's great. So in this type of modeling, the type of information you have, input information, is decisive. And so just let's look at the most important input data that we have. So we have the water gap low resolution output, and we use the surface runoff simulated by water gap, the groundwater outflow to rivers, and the overall stream flow for downscaling. But how can we downscale it? For downscaling, we need a drainage direction map. So how does the water flow from a 500 meter grid cell to the next? And that is available in the Global High Resolution Drainage Direction Map, Hydrosheds version 1 by Bernhard Lehner. Without that, we wouldn't do anything, because that tells us how water is flowing over all of Europe. And then the other essential time data set that we put a lot of work in to bring it together is a time series of observed daily stream flow at 3,706 gauging stations all across Europe. And there was a previous effort to also find intermittent stations, because generally intermittent stations, so stations where the water doesn't flow every single day, there are not so many, because these are not at the focus of, let's say, water resources and water supply. So, so we found also these 885 intermittent stations. And then, of course, in addition to those high resolution stream flow estimates, we also use high resolution data on physiogeographic conditions such as aridity, slope, karst, how large the drainage area is, and also, for example, land cover as additional predictors, static predictors. Next slide, please. Just to give you an impression about the first input, this is the output of the global model water gap. So global hydrologic models combine global scale data with process knowledge. So it's different from a random forest modeling that it's a data-driven, very data-driven model. So you don't think about processes, but with water gap computes for all land areas of the globe, the water fluxes such as runoff, actual evapotranspiration, stream flow, and groundwater recharge. It computes water storages in snow, soil, groundwater, surface water bodies. And it computes human water uses because, of course, how much water is in the river is affected also by human water abstractions. And we take into account, but unfortunately that can only be done in a very rough manner, the impact of human water use and man-made reservoirs on water fluxes and storages. And on the right-hand side, you see this map, just a section from the globe for North America, and it gives you an impression what a half-degree resolution is. So this yellow area in the center, that's the Mississippi Basin, and you see the drainage directions, how water flows from one grid cell to the other. So that's a half-degree resolution. And now with such a resolution, I mean, of course, you can try to assess intermittence, but intermittence occurs mainly on the smaller rivers. I mean, not on a main river, particularly if you only have, so to say, in your model, one river in a 50 by 50 kilometer grid cell. And you saw also in Louise's presentation that is the main river in the Genal, for example, that is more or less perennial. So if we would, I mean, we have done that in the past, if we assess intermittence at this spatial resolution, only rivers in semi-arid areas of the globe have some intermittence. So to assess intermittence, and particularly in more humid areas, it is really necessary to go to smaller, to higher resolution, because in a way, in every single climate of the Earth, always the smallest, the most upstream reaches are intermittent. So it's really, intermittency is a scale issue. So we needed to scale down from this half degree. Next slide, please. And so we did the downscaling. I will not go into details how we did that. So, but we then derive from the water gap output this stream flow estimates at the spatial scale of 500 by 500 meters. Then we assign then to these 500 meter cells these 3,706 gauging stations. And then we compared the monthly time series, so the time series of monthly stream flow, to our model results. And this is the necessitative efficiency. Everything that is red, it's not doing a good job. It is not skillful, the model. But you see, you have quite a bit of green and yellow values that you think, okay, actually, I must say, as a global hydrological modeler, I was amazed, because normally we evaluate stream flow maybe for basins that are larger than 10,000 square kilometers, because our size is 2,000 square kilometers of a grid cell. And here we go down to upstream basins of 2 kilometers, 2 square kilometers. That's our smallest basins, or the most of them are between 50 and 500 square kilometers. And I was surprised that we do have some skill in downscaling. Next one. So we have this high resolution stream flow estimates, but monthly scale. And then can you click one more, Margot? And then in this red box, you see that we then derived a number of predictors for the random forest modeling based on the stream flow. Just at the top, just the monthly stream flow, but then we looked also at the mean monthly stream flow over the last 3 months, because of course that can have some impact. So we just came up with various predictors from the water gap stream flow. And then what you see on the bottom is mostly these high resolution static predictors that do not change over time, like how big is the drainage area to start with. And okay, maybe on top also we had some low resolution monthly time series, for example, the number of wet days that we also thought is an important predictor. So in a month, if you have just 1 wet day with rain, or if you have 15, that makes a big difference, we thought, on intermittence. Next one. So I will not go into details. But we set up a random forest modeling workflow that it's a two-step workflow. So the most important part is, unfortunately, I don't have a mouse now to show you, but can you click? Yeah. So you see here, in the first step, we just try to predict if a month is perennial or not. So if that month has just 1 day of no flow, because in Europe, there are many more stations that are perennial and many more months that are perennial. So it's better to just first predict that. And then in the next step, can you please click? Then for only those months that in the first step have been identified as intermittent or observed, then we try to estimate how many days in the month are without flow. So we do not try to predict it for every single day like Louise did for the small basins, but we just have 4 classes. So as I said, 1 to 5, 6 to 15 days in this month, 16 to 29, or the whole month. And so we set up these 2 random forest models in a sequential way. And then once we have set that up, we can then apply that to predict for all the stream reaches. Next, please. So on the left-hand side, you just see observations. So just from the 3,700 observations, what is the percentage of observed intermittent months? Everything that is gray is there, that is a perennial river all the year. And then in red, you see, in red also, but mostly in blue colors, you see the percent of observed intermittent months on the left-hand side. And 24% of the stations have at least 1 no-flow day. And then when you look at only those stations that have intermittent conditions, then the median percent of observed intermittent months is 5.6%, and the mean is something like 16%. Okay, so that's just the observations that we use for setting up the model. And then on the right-hand side, on the top, you see the ratio of the predicted no-flow months divided by the observed no-flow months. And what is very clear is that we do have an observation of intermittent months in the semi-arid areas where you do have a lot of intermittents, and then on top we overestimate it, and that we explain it to that in those basins also our model, our downscale stream flow was not very good. And so why is that? Because in semi-arid areas, like also in Sardinia or Cyprus, but here in Spain, there's a lot of human water management. Particularly, people have produced a lot of storage, artificial storage in reservoirs, small and large reservoirs. And while we have the very large reservoirs in our model, it's still difficult to predict how people really make decisions on how to run the reservoir. Anyway, we overestimate the intermittent months. What we see in the bottom slide is that we have a good representation of interannual variability of intermittence, which is a good sign, it's good for being able to predict climate change impacts. If you can see the impact of climatic variations from year to year on your intermittence. Next one, please. So in this, from the random forest modeling is a machine learning method or artificial intelligence. That's how they call it. But what is good is it's an explainable AI, not like deep neural networks or wherever, where you don't know why you get some results. Here with random forest, it's nice that you get from the model and the importance of predictors for identifying intermittent months. And I showed just the results for the step 1 model, where we just predict if a month is intermittent or perennial. And what you see very clearly here, the most important predictor is the drainage area. So the smaller the drainage area, the more likely is it that a stream flow is intermittent. This just comes out of these 3,700 stream flow observations. But then the next 2 predictors are the monthly time series of stream flow or this is what is the second one, Q, or the mean monthly stream flow over the last 3 months. And then the fourth one is the slope. And the fifth one is the aridity. And so it goes down like that. So it really, you understand, I mean, you can see what is the cause of intermittence. Next one. So in the next one, we come back to one of our major results. Just now, I think you can understand better how we came up with this colorful picture. What I can tell you is that what we also see in our results is a clear seasonality of intermittence. When you aggregate over all of Europe, we have the lowest number of perennial reaches in July and the highest in January. So, I mean, this is what we expect if we aggregate all over Europe. So also here we think that, I mean, it makes sense. I mean, it's not that with random forest modeling, you might end up with something very random, but it's not the case. I mean, you come up with explainable results that at least give some, give some explainable results. Okay, my last slide, can you please change? Is the outlook. So we will very soon start in estimating potential future climate change impacts on streamflow intermittence in Europe. And how will we do that? We have already done with water gap climate change runs. So we already have runs available where water gap output, so the runoff and so on, how it is developing over the 21st century under those different emission scenarios that also Louise mentioned. And then this output of water gap will then again be downscaled to get downscaled to high resolution monthly streamflow time series with using also the 4 GCMs that are available in EasyMap. And then we will apply again then the random forest model. So just apply, so that will be very quick. We will apply the random forest model to estimate changes in the occurrence of streamflow intermittence. Yeah, that's all for me, and I'm looking forward to your questions or also comments.
Okay, thank you, Petra and Louise. So sorry, we don't have a lot of time left, but please feel free to ask if you have some questions for Louise or Petra.
And we can also, if you want, stay a little longer, because not a problem.
Well, I guess the presentations were really clear.
Yeah, just turn on your mic and ask a question or give a comment. You would also turn on your camera, so we see each other. That also might be nice for a discussion. Maybe it's a little difficult when we're just having these blank symbols. And I think when people turn on the camera, then maybe it's easier to ask. So. François already told us a nice presentation. Thank you. So thank you that you liked it. This is it. Please speak up. A webinar is about like a seminar. A webinar just means that then there is some discussion, not just.
Hello, everyone.
Hi.
Thank you for your presentations. I have a question on how do you think about human feedback when you do climate simulation? Because sometimes you can have no more water at all, so you can't do the same pumping of water. And maybe with the climate changing, you will have more pumping, so you can have both cases. So how do you think about that in your future research or current research, for Louise?
So regarding the study of the 6 European study cases, we are thinking of, yes, maybe exploring some water abstraction and also catchment management scenarios. We could also, with the J2000 model, explore some scenarios of land use change and also perhaps some water abstraction. The main difficulty on water abstraction is that actually we do not have even the data on the present time period. Well, not detailed enough data to simulate the abstraction very precisely. So then to run some scenarios, it's a bit complicated, but it's something that we could technically do with the model, but then we have to explore how to get the data to validate the model in the present period and also to construct the best scenarios in the future.
And for the European scale, I mean, while our model does include human water abstractions and also dams, we think that for this high scale, this high resolution intermittence modeling, it doesn't make much sense because our scenarios only work then at the half-degree scale, so for the big rivers. That's also the reason why we're not doing a good job in Spain, because when you think about you have a 50 or 55 kilometer grid and then we go down to 500, every single weir that is somewhere in the landscape will have an impact. Every single, I mean, we do have also small scale reservoirs, but they are not connected to each 500 by 500 meter grid cell. We only have it as a percentage on a half-degree grid cell. So I think at our scale, it is impossible to meaningfully include human impacts in the future at the current state of data.
Both your responses.
Thank you. So.
Is there any other question? I do have one. I think Petra just elaborated now that my question was about I don't know, maybe if you could elaborate a little bit more on how the model is not doing the best job in Spain and how is the human impact already taken into account in the random forest as it is now, and
yeah,
I don't know how.
Yes, I can do that. In hydrological model, the problem is that those areas where water quantity is the most important or where water stress is the highest, that is the areas with little precipitation and high evapotranspiration, so semi-arid areas of the globe. First thing is hydrological models are doing always a better job in humid areas than in semi-arid areas. Why? Because in the semi-arid areas, a larger part of the water of the precipitation evapotranspirates, and only a tiny part is left over to be the runoff that then can go into the streams. So that's unfortunate, so to say, but that's the physics. And then in the semi-arid areas of the world, people have tried to change the natural flows to store the water. So they have interfered with the natural cycle more than in humid areas. So in our global water model, we take into account many thousands of man-made reservoirs that exist around the globe. But first of all, the database for that is in some parts of the world very poor. For example, in China, we do have some information that we got, so to say, illegally out of the country, but there are many, many reservoirs that are just not included in the database that are globally available. And then, like say for Europe, I mean, we do have more or less not a full account, but from the larger, we do have that full account of the reservoirs. But then when you think about your reservoir manager, a dam manager, the decisions that you take, so I mean, they decide every single day how much water they let out of the river, out of the dam, out of the reservoir into the river. This is a very subjective decision that is very difficult to simulate based on some algorithms. I mean, we try that, other people try that, but it doesn't work well, many cases at least. So now in the future, for example, we will calibrate that more with new remote sensing data. But then this is just at the half-degree scale. And when we go down to by a factor of 14,000, then unfortunately, we do not know where on these small streams people have built some dams, or even just weirs that also have an impact, just those tiny little structures that impact on intermittence, on no flow a lot. And then on top, of course, you have the water abstractions that, for example, you have water abstracted from the groundwater. They also affect the streams. And then because they draw down sometimes the water like in the figure that Louise showed, no? It takes out the water from the river into the groundwater sometimes, or at least decreases that. Okay, so that's the reason why in the areas where you most have intermittence and where the quantity problems are highest, the models perform worse. That's how it is, I would say.
Okay, thank you.
Okay, I think then.
Okay, well, if there is no other question, maybe we can stop here. Thank you all for attending. And for information, the next webinar, the next DRYvER webinar will take place still online on November 15 from 11 to 12 also. We will send out the link very soon. Thank you. Have a nice day.
Okay, thank you. Bye-bye.
Bye. Thank you.
Thank you very much. Bye.
Thank you. Bye-bye.